Now we'll learn a very interesting thing, that is calorimeter. Calorimeter. It is an instrument by which we can able to measure the heat energy absorbed or reduced by our body. So to measuring the temperature from very childhood age, we have written one difference between heat and temperature, that calorimeter is used to measure the heat energy and thermometer is used to measure the temperature. I think in class 7 we have written this difference, and there what is thermometer that we have learned, but what is calorimeter that time teacher has told you that you will learn it later. So that is the time, this is the time when you can able to learn what is calorimeter. So if I'm talking about calorimeter, it is nothing but a copper container. It is a copper container which is covered by a wooden box. Okay, and here in the box there are two holes, one, two, and here no holes there. What is the purpose of this two hole? From this hole, one thermometer is moved inside it. Okay, so it is a thermometer, and from here one stirrer. What is stirrer here? See, sometimes some guest has come to your home, then your mother is making a juice by using the spoon as a stirrer, mixing the sugar with the water. Okay, uh, maybe the lemonade whenever she has made it. So this is being formed here. Okay, and this gap, it is full by wools, dust. Okay, dust means the dust of woods. Okay, by that insulating material, so that heat cannot able to go outside. So it's a copper container, and inside the copper container, that is water. Okay, and it is covered by a wooden box. Okay, and there in the gap between the container and the box, the wools are kept. How it works and why we have used copper? How it works, we will just learn little later. But the condition is why we have used copper. If I am telling the basic idea of measuring heat energy by it, simple thing is that open the box, and what's in which product heat energy you have to measure, just put it inside the water. Okay, it may be a heat energy of an iron rod, it may be the heat energy of a iron ball, a copper ball, or maybe a heat energy of ice, whatever the material may be. But we have to remember that that material should not make any sort of reaction with the water. If it makes any reaction, then additional heat is produced, so then the exact heat we cannot able to measure. So we have to put that substance and we will stir it with the help of the stirrer, and then we have to measure the heat energy. Now first I am coming to the point, why copper? See, we have just seen the specific heat capacity of copper is 399 joule per kg Kelvin, and we have seen it is comparatively very low. Low specific heat capacity means, low specific heat capacity mean it can easily change its temperature by getting less amount of heat energy. That means what substance I have put it inside the water, then the heat energy or the temperature of the water is changed due to the substance I have put inside. So what temperature of the water should be there, that temperature will be the temperature of the copper container, that means the calorimeter. So our idea is, by getting less amount of heat energy, it can able to change its temperature. If instead of copper I have used any another material, then the copper substance or the container, it will absorb more heat energy, and if it will absorb more heat energy, then it is not good for our experiment. So our target is that this container will absorb less amount of heat, and the heat should be transferred in between water and the substance I have put inside. Now the second question is, why water? What is the need of water? Again I am telling, the specific heat capacity of water is for 4200 joule per kg Kelvin, which is very high. In which reason I have taken copper to make the container. For the opposite reason I have taken water. Why it is opposite reason? The opposite reason is that, assume you have putting inside one iron ball whose temperature is high. Okay, the temperature of water is 25 degrees centigrade, and the iron ball you have put it inside, its temperature, assume it is 95 degrees centigrade. Okay. So as they will come closer together, the temperature will be changed. What will happen? Now whose temperature is low, the water, it will take heat energy from the iron ball, and the iron ball will lose its temperature. Now what is the basic significance of this instrument? Now the heat energy absorbed by water, that should be heat absorbed by water, not change the temperature rapidly. So the temperature will change of water, but it will not change rapidly. There is no abrupt changes occur. That means it will absorb more heat to increase a very less amount of temperature, because the heat absorbing capacity of water is more as the specific heat capacity of the water is more. So due to that, I can able to measure a heat energy for a long range. Okay, as I have taken water here. Okay, so simple reason. Copper we have used, as its specific heat capacity is low, it will just change its temperature to the temperature of water. That means what should be the temperature of water? That will be easily changed for the temperature of the calorimeter. Same temperature it will come by getting less amount of heat energy, as its specific heat capacity is less. And in another sense, if I am talking about water, it will absorb huge amount of heat energy to change very less temperature change. So that's why the heat absorbing ability of water is more, so that we can measure a huge range of heat energy. So that is calorimeter, and why this cover has been given, so that no heat is been radiated from the copper surface. What is done, the surface of the copper container, it is polished, so that if any heat also come from outside, it can able to reflect it. It is polished. Okay, so it can able to reflect it, so the effect of atmospheric heat energy, it will not come here. That is, the radiation effect is prevented due to the polishing surface of the copper container. And in another side, as there is wools, so it is fully insulated material, so no heat from inside cannot able to go outside by conduction or convection process. Okay, conduction and convection you have read in class 8. Okay, so I think this is clear enough for calorimeter. Now the next question, how the heat energy should be measured by calorimeter. How the heat energy should be measured by calorimeter. So to measure the heat energy by calorimeter, we have to learn principle of mixture, whose another name is principle of calorimetry. What it tells, what is the significance of principle of mixture or principle of calorimetry? First of all, I make you clear why we have taken this word mixture. So if you see the calorimeter, here I am mixing another substance to the water so that the heat energy should be changed. Why? Why the heat energy should be changed? Now, hot body, simple thing, hot body will release heat energy. Hot body means which is hot body inside the calorimeter, and cold body will absorb the heat energy. This thing will occur if you put here a substance of 95 degrees centigrade. Definitely the water will absorb heat energy from it and it will radiate heat energy. Okay, so hot body will radiate heat energy or release heat energy, and cold body will absorb heat energy. Instead of this body, if I have taken another body of 5 degrees centigrade, for this body, water is hot body there and it is cold body. So hot body means water will release heat energy, will radiate heat energy to cold body, and cold body will absorb the heat energy from the hot body. So based on this principle, we can able to find the heat energy. So that principle is principle of mixture or principle of calorimetry. Okay, what it tells us? It tells that if no heat energy is lost, then heat absorbed by cold body should be equal to heat release by hot body. That means if by any way no heat energy is lost, then the total energy should be conserved. It is nothing but the energy conservation law. Energy conservation we have read in the previous part, means in work part energy conservation. So energy cannot be created, cannot be destroyed. Here also we have seen that heat, as it is a form of energy, so if no heat is lost, then heat absorbed by the cold body should be equal to heat released by the hot body. These two things, this two heat energy should always be same, and based on this principle we can able to measure the heat energy of any body by using calorimeter. Okay, so next we will do the mathematical expression of calorimetry. Okay, so mathematical expression of calorimetry means here we have to express principle of calorimetry mathematically. Yes. So principle of calorimetry, what it tells us? It tells us heat lost by hot body or heat released by hot body should be equals to heat absorbed or heat gained by cold body. Okay, let two bodies, okay, sorry, two substances we have to take. Take A and B. Two substances we have taken, A and B. One, if I'm talking about A, its mass is, if I'm talking here mass, its mass is MA and the mass of B is MB. Okay. Specific heat capacity. So for A it is Ca, for B it is Cb. Temperature, for A it is Ta, for B it is Tb. Let Ta is greater than Tb. Okay, so if you mix it together, which body will release heat? Definitely A body will lose their heat energy because its temperature is more, it is hot body, and Tb it will absorb, means the B body will absorb the heat energy, its temperature is less. Okay, so if you put it or keep it together, they will get a constant or a final temperature. So Ta and Tb, they are different temperatures are there. Okay, so if you put it together, okay, the temperature of mixture after some time is equals to T. Means whenever you mix A and B, when you keep together A and B, after some time the temperature will be T, and the T temperature is for both A and for both B. So if I am talking about T, then it is greater than Tb but less than Ta. Mean it is a moderate temperature in between these two. Okay, that means how much heat lost by body A or the substance A. Heat lost by the body or the substance. Let's write substance, it is better, appropriate, not body. Substance A. How much? Assume that one I have taken QA. That should be, we know total heat Q equals to mc del T. So here mass is Ma, specific heat Ca, and temperature change del T is what? Temperature change. So how much temperature is changed here? Initial temperature is Ta and now the final temperature is T. So this is the temperature difference. This is the temperature difference where T is what? This T is final temperature. So QA equals to MA CA TA minus T. Heat gain by substance B. Heat gain by the substance B. We have taken this one QB. It is MB, CB, Now change of temperature. Change of temperature is, see, its initial temperature is TB, but now the temperature is T. That means here the temperature is increased. Here for the body B, the temperature is increased. So T is greater than TB. We have already written here. It is T minus TB. Okay. This two heat energy we can write as per principle of calorimetry. QA equals to QB. If QA equals to QB, we have to write MA CA TA minus T should be equals to MB TB. I'm sorry, MB CB TB or T minus TB. These two heat energy should be same because heat lost by the hot body should be equals to heat gained by the cold body. Okay, so this represent the principle of calorimetry in mathematical form. And here you see, if any temperature is unknown to you, that you can able to find if the rest of the things are given to you. Okay, if the rest of the things are given to you, you can easily find out which one is unknown. In your book, maybe instead of MA, it is written M1. Instead of MB, it is written M2. It is C1, it is C2, it is T1, it is T2. It is given in your book. So here, all the things should be same. M1, C1, T1 minus T should be equals to M2 C2 T minus T2. Rest of the things are same. Okay. So whether we have taken A, B or 1, 2, it is not important. Simple thing is that heat absorbed by a body should be equal to heat absorbed by a cold body should be equal to heat lost by a hot body in a mixture where the heat is not lost by any other process. Okay. Now, whenever we have taken into account the calorimeter, then what will happen? Let's see. In the previous part, we have learned about the calorimeter. Okay. So, as we have learned about the calorimeter, then calorimeter is one of the body. It can also absorb or reduce heat energy. Okay. It is kept inside a wooden box. Okay. And here the woolen substance or woolen materials or insulators are given, whatever. And assume the water is kept inside it. Let mass of water is M1. The water inside it. Mass of calorimeter is M. Okay. And temperature of water and calorimeter is equals to T1. Okay, so three things I have taken. Mass of water is M1, mass of calorimeter is M, and temperature is T1. No problem with that. Now I have put one substance here. So assume mass of substance is equals to m2, temperature of substance is equals to T2. Okay, it is kept inside it. It is M2, its mass. It is putting inside it. So definitely the substance will lose heat because its temperature is more. If I have written that if T2 is greater than T1, T2 is greater than T1, then substance will lose heat and water and calorimeter will absorb, and that too should be same, that is equal. Initially we have taken that one body is losing heat energy, another body will absorb the heat energy, but here substance will lose heat as it is putting inside the water. Who will take the heat energy? Now the heat energy is taken by water and the heat energy is taken by the calorimeter too, because it is also a metal substance which is made by copper, so it is also absorbing the heat energy. Okay, so talking about the specific heat capacity. So specific heat capacity of water, let's take it C1. Specific heat capacity of calorimeter, let's take it C. And here specific heat capacity of substance equals to C2. Okay, now heat lost by the hot body. So hot body is the substance, heat lost by the hot body. So here hot body is what? Hot body is substance. So let's see how much heat is lost. Heat lost by hot body. But before calculating the heat lost, I have to find out what is the final temperature. So let final temperature is equals to T. What is final temperature? That as you have put a body inside it, then hot body will release heat energy and cold body will absorb, and by that the temperature should be constant, and that can be measured by the thermometer. So final temperature is T, which is less than T2 but greater than T1. Okay, so now heat lost by the hot body, we can able to find it, that is Q2 equals to M2 C2 T2 minus T. See, in previous calculation T2 is less, now in this calculation T2 is more, so that's why M2 C2 T2 minus T. Coming about heat gain by cold body. So here you see how many cold bodies are there. So heat gained by cold body is not there, it is cold bodies. How many cold bodies are there? One, it is water. Another, it is calorimeter. Means the instrument itself, the container itself. Okay, calorimeter means I am talking about the container itself. So how much heat is gained? Q equals to, if I am first talking about water, it is N1 C1. What is the temperature difference? Now it is T minus T1, because final temperature is T, initial temperature is T1, so M1C T minus T1. If I am talking about calorimeter, that should be added also because it is also absorbing heat, that is MC. Its temperature is also changed same. Its initial temperature is T1, Now its temperature is T, so it is T minus T1. If I take common, T minus T1, if it is common, then it is M1 C1 plus MC. Okay, many thing is done. Now, as per principle of calorimetry, as per principle of calorimetry, heat gain by hot body, heat loss by hot body should be equals to heat gain by cold body, that is Q2 equals to Q, that is M2 C2 T2 minus T should be equals to M1 C1 plus MC T minus T1. Okay, just see the calculation from where it has come. See, it is exactly same with the previous. It is exactly same with the previous thing we have done. In the previous case, we have taken only two bodies. But here, there are three bodies. One, the body you have kept inside the water. Water, it is itself a body, and the calorimeter, the container, it is also a body. So what heat is lost by the hot body of mass M2, that heat is gained by both water as well as the calorimeter. Okay, and that's why you see here, very interesting thing you have to remember, that what is the temperature of water, that same temperature will be for the calorimeter. Here also, when the temperature is changed to T, then the temperature of calorimeter is also changed very faster, and for that reason only we have made the calorimeter by copper. If I have taken any another substance, then this thing will not happen. I know this calculation is not very easier, but first if you understand that by which principle we have done, that is principle of calorimetry. Maybe in this part I just want to write everything in one board, so that's why the handwriting is not proper. If you try to understand, you will get it. Okay, thank you. So as we have discussed about calorimetry earlier, now we'll do some numerical from the exercise questions. So I'll just choose 3 or 4 numericals I'll do, and rest of the questions you will do it by your own. So we'll start numerical from exercise 11A from your book Concise Physics. So exercise 11A. Numericals. So which numerical we will do it first? I'm going with numerical number 3. So first 1 or 2 numerical we'll do, it is little easier. Then we'll go the harder one. It is told a piece of iron of mass 2 kg. So what thing is given to you? Given mass M equals to 2 kg. Okay. Heat capacity. Next thing, heat capacity, which is denoted by capital C. We have read it earlier. That is 966 Joule Kelvin inverse. Next, heat energy needed to warm it by 15 degree centigrade. Okay, so the temperature change del T is equals to 15 degrees centigrade. Now you may be asked, sir, how we can able to know the temperature change is 15 degree? If you read the question, it is told heat energy needed to warm it by 15 degrees. So we have to increase the temperature by 15 degree. So it is simply the temperature difference. Now it is told to find the heat energy. So heat energy Q is equals to M into C into del T. Again, we all know that, we know capital C, that is heat capacity, is equals to m into small c. Heat capacity equals to mass into specific heat capacity. Here capital C equals to heat capacity, that is equals to mass into specific heat capacity. So mc del T, that can be expressed by this way. Instead of mc we can write C into del T. Okay, C into del T. Okay, now we'll go for how much temperature is changed or how much heat energy is absorbed. Okay, heat capacity C is 966. Temperature difference, it is 15 degrees centigrade. Now you may be asking that, sir, heat capacity here Kelvin and temperature difference is 15 degrees centigrade. Should I use 15 or we convert it into Kelvin? I have told earlier also, temperature difference in degree centigrade is equals to temperature difference in Kelvin. Okay, so as we are talking about difference, we will not change it. We will just keep it 15. So multiply it, 15 6 are 90, 0. Okay, 9 is in our hand, 15 6 are again 90. So 90 plus 9, 99, again it is hand. 15 9s are 135 plus 9, 144. So it is 14490. This much amount of joule of heat energy is needed to increase the temperature by 15 degree centigrade. Okay. Now the next question, it is coming, the first question, coming to question number 2. What is asked here? Question number 2, that specific heat capacity in SI unit. It's very easy thing. See, we already know capital C equals to small m into small c. Specific heat capacity means you have to find small c. So small c is equals to capital C by small m. What is the value of capital C? 966. Value of small c? 2 kg. Divided 2 4s are 8, 2 8s are 16, 2 3s are joule per kg Kelvin. Okay, so that is the specific heat capacity in SI as it is coming in joule per kg per Kelvin. Okay, so this is question number 3. I think it is very easy and you can able to understand very easily. Now we'll go for the next question. If you write it down, if you want to write it down, pause the video here and then write. Next we will go for, let's see, I think question number 7. It is a bit interesting. Okay, question number 7. Maybe I am here doing little faster, but you have to do it very carefully. What is told in question number 7? 4, 5, 6, 7. Okay. Electric heater of power 600 watt. Power is given. How much? 600 watt. Raises temperature of 4 kg of liquid. So mass is already given. How much? 4 kg of liquid. How much? 10 degree centigrade to 15 degree centigrade. So del T, it is clear, 15 minus 10, that is 5 degree centigrade. Okay, temperature is raised, so temperature difference we will got because it is needed in 100 seconds. So time T equals to 100 seconds. So here it is, del T is the temperature difference, here T is time. Next, calculate the heat capacity of 4 kg of liquid. Okay, and the specific heat capacity of liquid. Two things, heat capacity and specific heat capacity. Now you see, two things you have to see from here. Power is given, time is given. So from here, can I able to find out total energy? because later you come to know, but here also you know that work done is equals to power into time, and how much work you have done, that will be the energy. So E equals to P into T. So total energy E, that is equals to P into T. So what energy is given by the heater? That is the heat energy. So instead of E, we can write Q. So Q equals to P into T. So what is the value of Q here? Q is power 600 into time 100. So we can write 6 into 10 to the power 4 joule. This much amount of heat energy is given by the instrument, the heater. Okay. Now it is asked, you have to find the heat capacity. So first one, number 1, heat capacity. So heat capacity, we know capital C is equals to small m into small c. Okay. Capital C is the heat capacity, small c is the specific heat capacity. Okay. And we know total heat Q equals to m small c into del T. And from here MC, that is equals to capital C. So Q equals to, I can say, C into del T, where this C is capital C, that is heat capacity. And from here we can write capital C is equals to Q by del T from this equation, as C equals to M into small c, and here Q equals to MC into del T. So instead of MC, I can write capital C, and where this capital C is nothing but heat capacity. And from here C equals to Q by del T. See, Q, you know that it is 6 into 10 to the power 4. Del T, temperature difference, it is 5. Okay. So here it will be 60 into 10 to the power 3, 12, 5 12s, so 12 into 10 to the power 3, it is joule. Okay, per, we can take, it is Kelvin. Joule per Kelvin. 12 into 10 to the power 3, joule per Kelvin. Okay. Now the next thing is specific heat capacity. Specific heat capacity. So specific heat capacity, that is equals to capital C equals to M into small c. So small c equals to capital C by small m. What is the value of capital C? 12 into 10 to the power 3. What is the value of M? 4. So 3 into 10 to the power 3 joule per kg Kelvin. Now you may ask, sir, temperature difference is degree centigrade. Why I am taking Kelvin here? Simple thing is temperature difference in Kelvin and degree centigrade as it is same, so we can interchange it. We can write joule per degree centigrade or joule per Kelvin. It doesn't make any problem. Okay, see the numerical, I think you can able to understand. Next, so if you want to copy it, pause the video here and copy it, and if you not understand, go again from the first, see the video again and again, you will understand it. See, here we have used huge number of equations, but if I am talking about the numericals, these are very interesting and easy. If you think it is hard, then it will be difficult for you, but if you think it is very easier, then it will be the easiest numerical of the whole book I am telling here. Coming to the question number 11. Now I am going little bit of difficult, not difficult. Here we are using principle of calorimetry. What it is told? 200 gram hot water at 80 degrees centigrade to 300 gram of cold water at 10 degrees centigrade. Neglecting the heat taken by the container, calculate the final temperature. Okay. Mass of hot water equals to M1, that is equals to 200 gram. First we have to write it. Next, specific heat capacity is equals to C1, and that is, as it is water, C it is given 4200 joule per kg per Kelvin. Joule per kg Kelvin. Now you see one thing, very interesting thing this is. Mass is given in gram, and when we are talking about specific heat capacity, here it is given joule per kg Kelvin. Now what we have to do here? In this case, we will do what? We will just change kg to gram. We have to just change kg to gram. So 1 kg equals to 1000 gram. If you do it, it will come 4.2 joule per gram degree centigrade. Now you may ask, sir, previously it is Kelvin, now how it is degree centigrade? I am telling the same thing. The temperature difference in degree centigrade and Kelvin, it is same. So we can write like this way. What is the temperature? T1. It is for hot water. The temperature is given 80 degree centigrade. 80 degree centigrade. So first part is done. Mass of cold water. So here we are talking about cold water. Its mass M2 we are assuming. So mass M2 equals to how much? As per book it is given 300 gram. C2, it is also water. So here also it is same, 4.2 joule per gram degree centigrade. And now temperature T2. T2 is how much? 10 degree centigrade. These two things you have mixed. So as you have mixed, so simple thing, hot water will lose heat or loss of heat, and cold water will gain heat. Okay. So we can say when this interchange will occur, after some time they will get their final temperature. Let the final temperature is equals to T. Final temperature is equal to T. So from here if I write as per principle of calorimetry. Now you may ask, sir, how we have to understand that here we have to use principle of calorimetry? When you have to see there is a condition of mixing something, there is a condition of mixture, then you have to use principle of mixture or principle of calorimetry. Same thing is there. So heat loss by hot water is equals to heat gain by cold water. And here one thing it is already mentioned that we will not take container into account. So container will not take or give heat energy here. Heat lost by hot water. How much heat is lost? Now mass of the water is M1. Specific heat capacity C1. Temperature change, initial temperature is T1, and after that the temperature is T. So it is clearly that T1 is greater than T is greater than T2. So T is the temperature at middle in between T1 and T2. So M1 C1 T1 minus T should be equals to heat gained by the cold water, that is M2 C2 T minus T2. M1 C1 T1 minus T is equals to M2 C2 T minus T2. Now we have to put the value. Okay, so M1, what is it? 200 into C1 4.2 T1 minus T 80 minus T should be equals to 300 into C2 is again 4.2 into T, it is T minus T2, so T minus 10. Okay, T minus T2 is 10, I have already taken. So T minus 10. See here, 4.2 will be cancelled out. 0, 0 will be cancelled out. Now multiply 2 into 80. So 160 minus 2T, that is equals to 3T minus 30. Take T here and another things will be this side. So if 2T is going there, so it is there 5T, and if it is coming, it is 190. So T equals to 190 by 5, 3s are 15, 8s are 38. So the temperature is 38 degrees centigrade. That is the final temperature. So we can write final temperature T equals to 38 degree centigrade. How easy it is, you see. It is not a difficult one. It's a very easy thing. Just write which is hot, which is cold, apply principle of mixture, and see your answer has come. No problem. Next, we'll go for the next question. Okay, I think it shouldn't make any problem for you. If you feel some problem, then you pause the video and see this numerical, how it is done again and again. Then you can able to understand. I'm just trying to do the harder one. I'm going for question number 12 also. 11, 12, 13, 3 questions I'll do. Question number 12. The temperature of 600 gram cold water rises by 15 degrees centigrade when 300 gram hot water at 50 degrees centigrade is added to it. What is the initial temperature of cold water? First, I am telling you this question is asked several times in exam. This is a very important question of this chapter. So first we have to take, let the initial temperature of cold water is T. We are assuming. Okay. Now, what the things are given that we have to see. Mass of hot water. For hot water, we have to do first hot water mass M1 is equals to, you see, 300 gram. Okay. And temperature T1, that is equals to 50 degrees centigrade. One thing we are missing, specific heat. So specific heat for hot water and cold water, it is same. So we will mention the specific heat of water C. We know that the value, that is 4.2 joule per gram degree centigrade. If we not mention also, it will not make any sense, because whenever we apply principle of mixture like the previous numerical, then this C will be cancelled out, whatever. Next, mass of cold water. Cold water mass M2, how much? 600 gram. T2 that we have taken, it is T. Okay, T2 is taken T because initial temperature of cold water we have to find out, it is T. Now read the question again. The temperature of 600 gram cold water is raises by 15 degrees centigrade. That means whenever you have add this 300 gram of water, hot water, then the temperature is raised by 15 degrees. So we can say final temperature is equals to T plus 15. Why? Because the temperature of the cold water is T. When you add hot water, it is increased by 15. So now the final temperature will be T plus 15 increased by. So it is the final temperature. Now we will just do what we have done earlier. That is, principle of calorimetry. As per principle of calorimetry, you can write principle of mixture, that is heat lost by hot body equals to heat gain by cold body. Simple thing. Okay, so heat lost by hot body, how much? Mass M1, specific heat C. Okay, value is not needed. Temperature difference, what is the initial temperature? T1. Final temperature, assume the final temperature you have taken T dash. So T1 minus T dash. Okay, that is the heat lost by the hot body. Heat gained by the cold body, M2. Specific heat C, because both are water. And now temperature change, T dash minus T2. Okay, T dash is the final temperature and T2 is the temperature I have taken, that is for cold water. Now let's put the values here. Okay, for hot water, so CC will be cancelled out. Specific heat capacity of water is same. It is 300. T1 is how much? 50 minus value of T dash. Value of T dash is T plus 15. So if I put T plus 15, it will happen minus T minus 15. Right? So instead of T dash, I have given the value of final temperature, that is T plus 15. Coming here, M2, that is 600. T dash is T plus 15. T2, value of T2 is T. We have taken the value of T2 is T. So minus T. Okay. So many things will be cancelled out. 0, 0, 0, 0. Minus T plus T. Okay. 3, 2s are 6. Many things will be cancelled out. So here this thing will come. 50 minus 15, that is 35. Minus T, that is equals to 15. 2 into 15. So it is 2 into 15. Because 2 is here and here inside it is 15. So that means 35 minus T equals to 30. If you interchange, T equals to 35 minus 30. That is 5 degrees centigrade. So, initial temperature of cold water is equals to 5 degrees centigrade. This question I am definitely telling it will come any of your question of the general school test, whatever the unit test you are having, and it can come in the final exam also. This is a very favorite question of board. Several times this question is asked. Okay, see the question, and if you are having any doubt you can ask me, and if you want to pause it, pause the video here and do it. We'll go for the last one. We'll go for the last numerical, and if you see it, I think you can able to do all the exercise numericals are given there in your book. Question number 13, last one, but it is the easiest one. 1 kg of water contained in a 1.25 kilowatt kettle. So power of kettle is given 1.25 kilowatt or 1.25 into 10 to the power 3 what? Mass of water. Okay, mass of water is equals to 1 kg. Next, calculate the time taken for the body time taken for the temperature of the water to raise 25 degrees centigrade to the boiling point. Okay, very interesting thing. So temperature difference del T, it is given 25 to 100. So 100 minus 25 degrees centigrade. So that is 75 degrees centigrade. You have to raise this temperature. And next thing, the heat capacity C, specific heat capacity, small c of water, it is given 4.2, okay, joule per gram Kelvin. Now you can do one thing here. You see, mass is given in kg, but the specific heat is given in joule per gram. So either we can convert the mass into gram, that is one thing, but my suggestion is convert it into kg. So it will come 4200 joule per kg Kelvin. Okay, 4200 joule per kg. Nothing else. We have done nothing very hard thing here. Joule per gram degree or gram Kelvin. So if you convert gram to kg, 4.2 joule, gram equals to 1 by 1000 kg into Kelvin. 1000 will come up 4200 joule per kg Kelvin. Okay, this is the simple calculation we have done. Now, how much heat is absorbed? We know that heat Q equals to mc del T. What is the value of M? 1. What is the value of C? 4200. Del T equals to 75. So it is 4200 into 75. No need to multiply this much joule. Again, we know one thing. We know that heat energy Q equals to power into time. I have just told in the first question that energy, total energy is equals to power into time, and here Q is already given, power is given, you have to find time. So time equals to Q by P. What is the value of Q here? 4200 by, what is the value of power? 1.25 into 10 to the power 3. Okay, 4200 into 75. I'm sorry, 4200 into 75. So here 10 to the power 3 is there, and here 10 to the power 2. Only 10 will be there, and this two zeros will be gone. 5 2s are 5, 15s are, okay, and 2 21. Now 5 3s are 0.25, 0.25, okay, and then so if you calculate it, it will come 363 by 25 into 100. If you convert it, okay, so 25 4s are 12, 252 second. It will come in 252 second. And now if you convert it in minute, so just divide it by 60. So 60, 252, 4s are 240. So 12 is coming. So we can say it is 4 minute 12 second. Okay, so this much time is taken to give such amount of heat so that the temperature will be increased from 25 degrees centigrade to 100 degrees centigrade. So these are some important numericals of the first part of calorimetry. So please try the another numericals are also given in exercise and see the numerical in examples. Thank you.